Hello there. This is my second lecture of a series of lectures on linear power supplies. My first lecture was on a half-wave rectification power supply. This lecture will be on the full-wave rectifier center-tapped power supply. The following discussion and equations are for a power supply which uses a full-wave rectifier and a center-tapped transformer. See figure 2.1. The energy storage capacitor will not be considered at this time. Figure 2.1 shows the power supply circuit diagram, and figure 2.2 shows the AC voltage waveforms of section A and section B of the transformer with respect to the center tap. Note the 180 degrees phase between the two sections. This means that only one section is active at any given time. And this is shown in figure 2.3. That's the output waveform. Now, how does the circuit operate? We start first with the blue polarities. You have your positive here and your negative in here. And the primary is aligned with the secondary. That means you have those two little dots in here that indicate whenever you have a positive at the primary, you have a positive at the secondary right here. Yeah, when you have those blue polarities and your positive is here and here, D1 will be forward biased and it will conduct, and whatever is in winding A will be present at the load. So this peak in here is for D1 and winding A, and when the polarities are reversed, as we see the green ones, winding B will be in action through D2. And as we see, since we are not using a smoothing cap, the output is not smoothed. Now, before we start our equations, let's see what the symbol definitions of these equations are. Symbol definitions are going to be repeated in every given lecture because they are standard for all the power supplies that I intend to discuss. You have that IM, which is the maximum peak current. You have the VM, which is the maximum peak voltage. You have the IDC, which is the average load current. You have the VDC, which is the average load voltage. The VAC equals the rated secondary voltage and RMS value. This is what's written in the transformer. IAC, the rated secondary current, that's in RMS. It's also written on the transformer. The total power of the transformer, PT, that's in volt ampere. The PL, which is the load power, that's in watts. The VL, that's in RMS, the effective load voltage. IL, the RMS, in RMS, that's the effective load current. IT, also in RMS, that's the effective transformer secondary current. These symbols are standard for all the configurations that I intend to discuss. Okay, let's move forward. Now let's start with the equations. And like I said before, the storage element is not included. Therefore, what you get in the output are those half sine waves that are not smooth. Now we're going to analyze these equations and see how much we're going to get out of our transformer when we use such a configuration. The VM, that's the maximum peak voltage, will equal the root square of 2 multiplied by VAC over 2. That half of the secondary voltage multiplied by 1.4. The VDC, it is the area under that function, which is Vm sine omega t dt. When you find that area by integrating that half sine wave and averaging that area over t over 2, 1 over t over 2, you get your VDC, which equals 2 over pi multiplied by the maximum peak voltage, or Vm. And that equals, when I relate it to the VAC of the transformer, that equals to 0.45 of VAC. So a little bit than half of what's written in the transformer. That's what your meter should read when you put it on DC, across the load, of course. And that's equal to the same value that we had before in our first lecture for the half wave rectifier, to the same value of DC. And VDC also would equal to 0.64 of the maximum voltage. That's 2 over pi would equal to 0.64, 64% of Vm. IDC, okay, that's the average DC current, same thing, would equal 2 over pi multiplied by Im, and that's 64% of the maximum peak current. IAC equals Im over 2. What that means, that you are allowed to make your maximum peak current to be equal to 2 times the IAC of the transformer without exceeding its specifications. Why? That was analyzed in our first lecture, but that just to tell that those 2 secondaries, one will be operated one at a time. So while one was active, the other one was relaxing. And that allows you to double the current that's allowed to pass through these windings. IDC, which is the average load current, would equal therefore to 2 over pi multiplied by 2 times IAC, and that would equal to 1.27 of IAC. So the total average load current is allowed to be 1.27 of IAC without exceeding the transformer specifications. And this is a high current, by the way. That's the merit of this type of power supply, that you are allowed to have much current through the load. Where what we have for the half-wave rectifier was only 0.64 of IAC. So what you have in here is double what we had for the half-wave. Okay, let's have an example. A center tap transformer has the following ratings. IAC equals 2 amps, VAC equals 12 volts, total power 24 volt amperes. What is the maximum value of load resistance, Rmin, that can be used without exceeding the transformer rating? For the circuit and the waveforms that we saw previously in figure 2.1 and 2.2 and 3, we have the Vm equals, like we said before, root square of 2 multiplied by VAC over 2. So that means root square of 2 multiplied by 12 divided by 2, and that equals to 8.5 volts. So you'll have 8.5 volts peak voltage across the load. Im max will be equals 2 times IAC, and that means 4 amps. The minimum resistance in this case that you are allowed to have is 8.5 divided by 4, that equals to 2.125 ohms. Any resistance greater than this, that would be fine with the transformer. Less than that, that means you are exceeding the transformer specifications. The load power, now we need to calculate how much power is in the load, and that's in watts. And of course that has to be in RMS. And for all rectified sine waves that we have in here, it's a standard. The load voltage in RMS would equal to Vm over the root square of 2. And likewise for the current, it's Im over the root square of 2. And that equals to Vm multiplied by m over 2. And that's in numbers. 8.5 multiplied by 4 divided by 2, that gives us 17 watts. So those unsmoothed rectified sine waves that you got in the output, the total true power for it is 17 watts. That's what you're gonna get across your load, and that's the maximum that you can get out of your transformer when you use it in this configuration. Now the percentage of transformer power utilization, the PTPU, we have the VL in RMS, voltage across the load in RMS, and like we said, it's Vm over the root square of 2. That can be written also to the root square of 2 multiplied by VAC over 2. The whole thing is divided by the root square of 2, and that equals finally to VAC over 2. We already know that, but just another way just to write it. The IL in RMS, that equals Im over the root square of 2, and it equals to 2 times IAC over the root square of 2, and the total thing would be the root square of 2 multiplied by the IAC. Okay, that's the RMS value across the load. So the power across the load will be VL in RMS multiplied by IL of the RMS, and that equals to the root square of 2 divided by 2 multiplied by VAC times IAC, and that equals to 0.707 of VAC times IAC, which means that the power across the load is 71% of the total power of the transformer. Keep in mind that power of the transformer equals the VAC multiplied by the IAC. Okay, and that unit, of course, it's in volt ampere, but this is in true watt, and you're gonna get about 71%. So 70% is what you're gonna get out of your transformer when you use this type of configuration. And something worth mentioning here, this is exactly the same PTPU value calculated for the half-wave rectifier discussed in Chapter 1. The load requirement for the shape and value of current and voltages dictates the type of rectifier to be used. So that depends if you want higher voltage or lower voltage, or you want higher current or lower current. That dictates what you should use. Now we continue our analysis, but we are going to use our storage element now to smooth the output across the load. Okay, so when we use that storage element, we are going to stress the transformer a bit more. Why is that? Because the transformer is going to be operating for only a short duration, which is TC. That's the conduction duration. So whenever the voltage across the transformer from winding A or winding B exceeds the value of the storage cap, then the transformer starts charging the cap, okay, with high pulses like the one we see in here. Okay. Now the charge that put during this little time must be enough for the cap to supply the load for the rest of the half cycle. And of course, the charging current through the cap is not actually this neat, not with those 90 degrees angles that we see in here. But this is just to simplify our life and to make our calculation easier. So in here, using a capacitor in conjunction with a full wave rectification does not stress the transformer current as much as the half wave rectification. Of course, the VDC will increase in value and become smoother, and the IDC will also become smooth and shall be considered constant in all the following equations. So the idea that charging the cap in a short duration means that the peak of the charging pulse must be high. And we're going to see this in the following equations. So the equations, when a capacitor is used, are as follows. We have our VDC, that's the voltage across the load. It will be equal to the root square of 2 multiplied by VAC over 2. That's what we used to have as a peak voltage. Okay. Minus variable voltage divided by 2. And later on, we'll see how much ripple voltage we'll get. And the Q charge equals the Q discharge. That's for the cap. You charge the cap with a Q and you discharge it across the load with another Q in there. The charge and discharge quantities must be equal, and that means the pulse that you charge the cap with multiplied by the time. Charge is always equal current multiplied by time. So the I peak of that charging pulse multiplied by TC, that's the conduction time, the time at which the transformer will be charging the cap, must equal to your DC current, okay, multiplied by half of the cycle, which is T over 2. And the RMS in this case in the transformer, when we made our assumption that it's like that pulse that we've seen earlier, the RMS for such a waveform will always equal to that I peak squared, okay, multiplied by dt. So you are finding the area underneath that one in there. Just square the value of the peak, find the area underneath it, average it over the whole T and the whole thing under the root square. That means you got the RMS for such a pulse, which equals simplified to IP multiplied by TC over T under the root square. That's a standard formula or equation. IC equals C dV by dt, with IC is the capacitor current. The value of C in this case would be equal to IC dt over dV, or C equals, in our terms, the IDC, that's the average load current that you intend to have, multiplied by TC over 2 minus TC, T over 2, minus TC, and the whole thing is divided over VR, that's the ripple voltage, and can be simplified, of course, to IDC multiplied by T over 2 divided by the ripple voltage. That's the value of the cap. The ripple voltage equals to Vm, that's the maximum peak voltage, minus Vm sine, between parentheses, 90 degrees minus Tc over T over 2 multiplied by 180 degrees, close the parentheses. That's provided this Tc is greater than 0 and less than T over 4. Now, to make more sense and relate the previous equations together, a conduction duration of 2.5 milliseconds, that's a 45 degrees, shall be considered. So throughout the lectures, for all the type of configurations of linear power supplies, that 2.5 milliseconds will always be considered as a conduction time, as a conduction duration. Okay, the maximum IP, how much IP we are allowed to have, what is the maximum IP that we are allowed to have? Well, that would equals to the IDC multiplied by T over 2, that multiplied by T divided by 2 TC. And that equals in numbers to 4 times the IDC. So the peak current that you are charging the cap with is allowed to go as high as 4 times the IDC, or it has to be like that because the duration is short. The duration is short and must have the same charge in cap for charging and discharging. So the peak current for charging the caps must be 4 times whatever IDC you got in your load. Okay, that means the IT in RMS, how much the current in RMS that will be drawn out of the transformer would be equal to I peak multiplied by the root square of TC over T, plugging the numbers in there, that give us 1.41 of IDC. That's the IT in RMS. So that means IDC max that we are allowed to have would equal that IT in RMS divided by 1.4, and that give us 0.707, so about 71% of IAC. So you are allowed to have as much as 71% of IAC of the transformer. Can't have more than that without exceeding the transformer specifications. As we have in the earlier, for the half wave, we got only 0.35 of the IAC. So this is double of what we had for the half wave rectification. Now IT in RMS, just a reminder, always equals to the IAC of the transformer. Those two are equal. Okay. These are equal when the maximum current capability of the transformer is used. And this is, of course, very rare or impossible. When you have a storage cap in there and changing the waveforms of that transformer, this becomes impossible. You'll never get that IAC, full IAC out of the transformer. Okay, let's go forward. The last equation indicates a good transformer current utilization. That's when the 71%. As a matter of fact, it is double that of half-wave rectification circuit. Okay, let's see how calculating the ripple voltage. When we are assuming that 45 degrees and 2.5 milliseconds, you have the ripple voltage, which equals, plugging numbers in there, Vm minus Vm sine 90 degrees, T over Tc over T over 2, multiplied by 180 degrees. Plugging our numbers in there again, that would give us 0.29 of Vm. So I have about 30% of Vm are ripple voltage under these circumstances. Usually things are a bit better than this. This is a conservative, let's say, type of calculation. And C, as we said before, would be equal to the IDC, open the parentheses, T over 2, that's a half a cycle time. We deduct the conduction time of the cap, charging the cap TC, and dividing the whole thing over VR. And I believe we should plug a few numbers in here to make the equations meaningful. Okay, so that means when you are operating at 50 Hertz, okay, C would equal to the IDC multiplied by 7.5 milliseconds. Like I said, this is a 50 Hertz. When you are considered the line frequency to be 50 Hertz, so the duration, total duration would be 20 seconds for a full cycle. Half a cycle would equal to 10 milliseconds. And when you deduct 2.5 milliseconds a conduction time out of 10, you get those 7.5 milliseconds. You divide that by the ripple voltage, which is a 0.29 of the Vm. And plugging these numbers will give us finally a 0.855 of Vm. So your DC across the load, okay, will be equal to about 85% of the maximum peak voltage. Now percentage transformer power utilization when a conduction duration of 2.5 milliseconds are considered. We'll have the following. The PL max, that's the power across the load, it equals VDC IDC, and that means plugging the numbers be 0.855 of VM multiplied. Okay, we have first the VDC, how much VDC we got. We can relate it back to the VAC. 0.8855 of VM, which equals 0.855 multiplied by root square of 2 multiplied by VAC over 2, and that comes up to 0.6 of VAC. The IDC max, like we calculated before, or derived before, we have not calculated yet, derivation only. It's about 70%, 71% of IAC. Okay, now I'm multiplying those two together, that give us 0.42 of VAC IAC, which means you got about 42% of the total power of the transformer. So how much you get out of your transformer? You got the P of the load, power of the load, divided by PT, power transformer, multiplied by 100%, and that gives us 42%. So what you got out of your transformer when you installed, when you added that storage element, the cab, is only a 42% out of the capabilities of the transformer. This percentage equals the one found earlier. This percent equals that one found earlier for the half-wave rectification. These percentages are equal because the first type provides double of the present voltage and half of the present current. Next chapter we will deal with the full wave bridge rectification circuit, where the benefit of the previous two types exist. That will be in lecture 3. Okay, now let's have an example, which is standard for all types of power supplies. We are always using the same transformer to see the merits of each individual circuits for the same transformer. A transformer has the following ratings: IAC equals 2 amps, VAC equals 12 volts, P total equals 24 volt amperes. This transformer is to be used in a power supply which uses a full wave rectifier, center tapped of course, and a smoothing cap. The conduction duration is chosen to be 2.5 milliseconds, as we always do. So find the value of R min, the power of the load, PR, the capacitor value, the ripple voltage, and the VDC and the IDC max. So the maximum voltage will be equal to 8.5 volts. The ripple voltage be equals to 2.46 volts. The VDC will be equal to 7.27 volts. Now, what is the maximum current that we are allowed to have? Like we said before, we get about 71% out of IAC, and that equals to 1.4 amps. We are allowed to have as much as 1.4 amps out of the transformer without exceeding its peaks. The minimum resistance in this case equals VDC over IDC, and that comes to be 5.2 ohms. That's the minimum value of resistor you are allowed to use. The power across the load multiplying the VDC with the IDC max, that will give us a 10.2 watts. That's the maximum power across the load. The capacitor value will equal to about 4300 microfarad, and that's of course the IDC, which is 1.4 amps. That's the maximum we're allowed to have, multiplied by 7.5 milliseconds. Okay, the duration that needed for the cap to discharge. Okay, divided by the ripple voltage in here. That gives us a 4300 microfarad. And the power utilization of the transformer, like we stated earlier, but now we are plugging numbers in there, would give us exactly as we had before, the 42%. That's how much percentage you're going to get out of your transformer. So the capacitor value is high for this type of power supply, for this type of configuration. The capacitor value is high. It is 1.5 times that value used for the half-wave rectification. This is due to the higher DC current and lower ripple voltage. That's why we have a 4300 microfarad cap in there. Components ratings. The diode ratings, the reverse voltage must exceed the root square of 2 times VAC. The average forward current that allowed for that diode, that's the minimum, must exceed the IDC divided by 2. The capacitor voltage must exceed the root square of 2 multiplied by VAC over 2. So that's the winding. Let's say winding A, winding B of the secondary, okay, multiplied by the root square of 2. So this is the peak actually. You're going to get diodes that go much higher than that for the same price, of course, not much cost. Fuse ratings. Fuse type, it must be a T type. That's a time lag type of fuse. The fuse voltage must exceed the primary VAC, so whatever you are using, 240 volts or 120 volts or whatever, its rating must exceed whatever you are using. Fuse current rating equals to 1.25%, 25% as a safe margin. We are always throw it in there. Multiplied between the two parentheses, IAC, VAC, that's whatever you got at your load, or whatever you got from the transformer, sorry, that's transformer rating, secondary, divided by the VAC of the primary, so are reflecting back the current, okay. For the power supply of example 3 and 4 that we had earlier, with smoothing cap or without smoothing cap, it's the same fuse, because you are protecting the transformer. That's the idea, and you are using the maximum that you can get out of it. Plugging numbers in there, that equals 1.25 multiplied between two parentheses, 2 times 12 divided by 240. That's when you are using 240 volts as the main supply voltage. That comes up to be 125 milliamps. See chapter 4 for more on this. Yeah, this deserves discussion. We're gonna include that in another lecture on how such fuses are selected for power supplies. This is the lowest value of all types. The fuse value is the lowest of all types of power supplies. Why? Because the transformer is fully relaxed. It has 2 secondary windings, A and B, like we discussed before. One is active and the other is relaxed, and after that the other one active and the first one is relaxed. So this relaxes the transformer. That's the first bit. The second bit, that whatever magnetized energy you got across that transformer when a current passing through a given winding, the other one, when it operates, is simply just sucks that storage energy and reflect it back to the load, and nothing will go to the mains. Okay, so whenever any winding magnetize the core of that transformer, the other winding will demagnetize it. And that's why you are not going to see this on the primary side. That explains why you have such a low value for the fuse sitting at the primary. Okay, now let's see what we get to. We almost concluded our lecture. Few remarks: the capacitor values for this type of power supply is high. It is about 1.5 times that used for a half-wave rectification. 2 diodes were used, of course. Transformer utilization is poor. It's always the case whenever you alter the shape of the output. That transformer was designed to give a sine wave, and you alter it to start giving pulses, and that means you change the shape of the waveform, which means you are not going to get the most out of it because you are always dealing with RMS. Okay, this type of power supply provides high current and low voltage. We discussed that earlier. The average power RMS delivered to the load by this power supply equals that of the half-wave type, but the reactive power is much less. The fuse value is an indication of that fact. And of course, I add to that, no harmonics are present also. For that half wave, we had a lot of the fundamental frequency harmonics, because only one peak of the cycle, okay, was passing to the load. So you had much harmonics in that half wave rectifier. This one has none. Okay, it provides the highest possible DC current of all types. So we're talking about 71% of the ratings of the IAC of the transformer, which is considered high when a cap is used, of course. This concludes my second lecture on linear power supplies or conventional power supplies. I hope that was useful, and thank you for watching. If you have any questions, just please write a comment and I'll answer it when I have time. Thank you for watching again. Bye for now.